Okay, so this is work which is a little bit after a work we're doing with John. So I think I'll maybe say a bit about anecdotes of John first, for the theme of the conference. So I don't remember exactly when it was I met John now. It was a long time ago. He was a referee on our paper back in 2007 and was writing a news and views on it. And then I was meeting him in person. I think it was at this workshop we had in Cairns. And I remember he was going to see this museum on poisonous Australian animals there. And like ever afterwards, he was telling us this anecdote about he went to see this museum of poisonous Australian animals, and it was so large it probably would have been a smaller one if it was non-poisonous Australian animals. So I actually gifted him a book of poisonous Australian animals sometime later when he was visiting us for our the discussions at Macquarie. Um, so I visited him in Louisiana, I think a bit more than 10 years ago, and we're looking at ideas of how to do states which are more robust against a loss. So sort of generalizations of noon states and trying to make things robust against loss, if I remember it correctly. We had the various other papers that we worked on when he was visiting. The most recent one was, we're always trying to look at ideas for how to make use of the boson sampling. And so there's this idea of, can you use boson sampling for the something like quantum key distribution? And so we're working on that, and while he was here, and I had to go off and travel, and it wasn't quite finished at that stage, and so he's posting that on the archive after I left, and they submitted it to a journal, and the referees were complaining that it wasn't really boson sampling, but we were actually able to prove the security using other methods. So the paper ended up being published without anything about boson sampling in the title or anything. So that was back in 2021. So and I noticed, actually checking on the archive, he had some on the Google Scholar, he had a couple of papers in 2022. So no. So this one is sort of well, I guess the connection we can make is that we're having discussions about Dickie states while John was here, and this is quantum algorithms, and part of it is using ideas for how to construct Dickie states. So this is a sort of the different type of the research than they're mostly working on with John. This is trying to work out interesting things to do with quantum computers, and assuming that you have some large quantum computer which has the fully fault tolerant, and also that you're going to look at counting of Toffoli gates. So essentially sort of you you have Clifford circuits which can be simulated classically, and of course, so if you want to have something which is a real quantum algorithm, it has to have non-Clifford things. So a lot of the time people would traditionally talk about doing things with T gates, but with a lot of the way we construct algorithms, it turns out that it's the Toffoli gates which are really important. So these are the controlled not. And this is looking at an alternative type of application than people have often looked at for quantum computing, which is topological data analysis. So this was proposed by Seth Lloyd and co-workers about 5 years ago now, I think. But what we're looking at is actually sort of, can we look at demonstrate a case where plausibly a fault-tolerant quantum computer can solve it, whereas a classical computer would just be beyond its capability. So we think we have an example, at least in some case, which is sort of a bit of an artificial example, and then with more general cases, we can show that we expect there to be a large speed up, but maybe it might still be tractable classically. And here we go. Forward. All right, here we go. So this is analyzing data using topology. So there's what's called Betti numbers, which are giving you all sorts of topological features of the shapes. And if you have data, you can analyze the shape of the data just by looking at essentially points which are like on these surfaces. And this is demonstrating sort of that you have different types of topological features of things where you can have sort of, there's the usual idea of you can have something with a hole in it, which could be like a donut or a coffee cup, which is topologically equivalent. But then you can have all sorts of things like things with two holes or separated donuts or interlinked donuts and various shapes with inclusions in them and separated bodies and so forth. And there's all sorts of complicated features that you can have topologically. And these can be quantified by Betti numbers, which can tell you information about how many holes there are and how many separated bodies there are and so forth. And you have Betti numbers of various orders. And then when you're going to these higher order Betti numbers, it's sort of telling you more complicated features of these structures. And it might seem a bit weird to be talking about data analysis in terms of topology, but the way that it works is essentially you have a bunch of points which are your data points, and you can look at separations between your points and say if points are sufficiently close, then you can say that you're going to draw a line between them. And you can imagine sort of if you were starting from a shape, you could imagine, say, putting a mesh of points on it, and you could see then that you could use the construct a graph from which points were close to each other, and then your graph of those points on that mesh on that surface would be telling you what the features of the original surface were. And so that's kind of the idea of data analysis using topology, except you would just have the points. There wouldn't be necessarily some underlying surface. But this can actually give you some very interesting information. So for example, people have used topological data analysis to retrospectively analyze financial data. And so they were doing an analysis of the financial data before crash in 2007 and before the dot-com bust. And they're finding that there was features that they could find from topological data analysis up to about 200 days in advance of the crash. So that was suggesting that you could use topological data analysis to predict the crashes in advance. And there's, yes. And that's like and there's all sorts of different things that you can use topological data analysis for. So then now going to technically how you treat these. So sort of if you see here, looking at these sort of drawing lines in between these points to construct a graph, and then you can look at, say, simplices, which are sort of the higher dimensional generalizations of tetrahedra and so forth, so where you can have multiple points which are all connected by edges in your graph. And you can have what's called a simplicial complex, which is sort of constructed out of many of these simplices. And then when we want to start turning this into something we can analyze in a quantum algorithm, what we're going to do then is represent simplices in a quantum state. So this example here is where we have basically each qubit there is representing a node in the original graph. And then if you look at where the ones are, the idea is that every pair of qubits with ones on them would be connected by an edge. So this state with 3 ones would be a 3-click where you have each of those nodes connected by an edge. And then you can have a representation of the graph in terms of superpositions of all of these basis states that you're representing cliques. And then what you can do is look at constructing a Hamiltonian, which is going to give us information about the Betti number. And so it looks something like this, where each of these operators are essentially, it's like you're taking an initial state like this, and then you're erasing one of those ones. So you'd have a superposition of erasing the first one, erasing the second one, erasing the third one. And then you would have a sign factor in it as well. And that's essentially what each of those sub-operators in this Hamiltonian are doing. And as well, that G there is restricting yourself to things which are on the graph. So the original recipe for the quantum algorithm, as proposed by Seth Lloyd, was essentially you would prepare a superposition over states with K1s. You would simulate the Hamiltonian and estimate an eigenvalue and repeat to find a proportion of 0 eigenvalues. So this is sort of the general outline of what you would want to do, because I think I skipped the point here that the dimension of the kernel is telling you what the Betti number is. So essentially what you're wanting to do is estimate how many eigenvalues are 0 for this Hamiltonian. It's going to give you the Betti number. So what we've done is done a whole lot of improvements in every step of this, and to work out how many gates you would actually need for this sort of thing, as well as looking at specific examples of graphs to see what performance you would get. Okay, so the first part there is this Dicke state preparation problem, and then there's a whole lot of ideas of clique checking and better ways of estimating the numbers of 0 eigenvalues in the Hamiltonian. So the first part here is the Dicke state preparation. So this is a somewhat different scenario than what Gavin was talking about. So here, what we're allowed to have is actually entanglement with an ancilla state. So the standard Dicke state would just be, you have, for example, 3 ones out of the 6 bits, and in every possible permutation of 3 out of the 6 bits. But for the purpose of the estimating Betti numbers, you're allowed to have entanglement, entanglement with an ancilla. So you'd have this entangled with a psi naught, this entangled with a psi 1, this entangled with a psi 2, and so on. So if you're allowing that, then there's all sorts of tricks that you can use. So one trick that you can use, I think, that will also let you construct something which is not entangled. is to use a symmetrization procedure. So that's sort of related to the idea of a sort. So if you're trying to do, say, if you're familiar with sort of things like quicksort and so forth, these aren't actually suitable for quantum algorithms. So there's things called sorting networks, which you can apply for quantum algorithms, where you have a whole lot of inequality tests and controlled swaps in a fixed set of locations. And what this actually gives you is then, if you've sorted something, it's giving you a whole lot of bits which are left over, or qubits which are left over, which are essentially recording the results of all of these inequality tests. So what you can imagine doing is, say, start with equal superposition states on a whole lot of registers, and then you can sort all of these registers. And what you end up with is actually something which ends up being unentangled between that thing you just sorted and these qubits which are left over with these results of inequality tests. But this is all reversible. So you can take all of these qubits that you just generated from this sort and use them with something like this, and then essentially do a sort in reverse. And that's actually going to give you your Dicke state. So that does tend to be a bit computationally difficult, even though it has some quite nice complexity that's roughly going like linear in the number of qubits with some extra logarithmic factors. But what you can do, which is a bit more efficient, is to do an inequality test. So it's a similar idea in principle to part of what you're doing with the sorting, and is that you could say, okay, I'm going to have for each of these bits, I'm going to say I'm going to have a register which is in a superposition state, and then I can work out a threshold so that if you have a integer in that register above the threshold, I'm going to put a 1 there, otherwise I'm going to put a 0. And it's possible to choose that threshold in the superposition, which actually gives you a Dicke state, which ends up having much the same complexity, except nicer constant factors, and it has a much better chance of success. What's the, when does this go to? Sorry, I have 12 more minutes, okay. So the next part that you have here is, once you've generated a Dicke state, you want to try and check which are the cliques. So if you remember before, I was saying if you had, say, 6 bits and you had 3 ones, and you were wanting each of those ones to be representing nodes which were connected by edges. And when we're preparing the state, we don't want to just have all possible permutations of the ones in those positions. We want to only have the ones which are corresponding to cliques in the graph. And this can be something which is quite difficult to generate, because in many cases you'll find that the number of cliques is much smaller than the total number of the possible positions of the ones. And so what we can do then, though, is have a clique checking followed by an amplitude amplification, which gives us an extra factor, which is going like this n choose k, which is the number of basis states for the Dicke state, and this, which is the number of cliques. And I'll mention as well that you have this factor here as well, which is coming from just checking that something's a clique. And you're assuming that the way that you're being given the graph is you're given a classical list of edges, and you just need to run through this classical list of edges, and you can basically do a Toffoli for each edge there, and check that the bits all sum up to the correct value, which is this. k minus 1 over 2. And this is quite a different idea to what people often look at with algorithms for, say, looking for cliques in graphs, because this is often looked at in the scenario where there's a oracle that's telling you whether there's an edge between nodes, whereas here you're assuming it's explicitly given data. But when you're looking at evaluating the Betti numbers, this ends up typically being exponential in the number of edges. So just having a factor which is going like the number of edges here is not so bad. So then there's a few more parts to this. One is simulating the Hamiltonian. So this is linking back to this idea of linear combinations of unitaries, which you heard earlier. So this thing here with these various boundary operators can basically be written like this. So what this is telling you is that on the pth qubit, you're going to do an x, doing a z on the p minus 1 qubit and all the way back. So it's a string of z operators, which is going to give you a sign flip according to how many ones there were in your basis state. And as well, you want to have some clique checking in there. But the core thing here is this sum of Pauli strings. And this is something which you can construct with a linear combination of unitaries. Well, it is a linear combination of unitaries, but it's something you can work out with standard methods. So general idea with linear combinations of unitaries is you have some state preparation, then a controlled operation. So that operation would be that Pauli string. And then you would have an inverse preparation. And if you were to project onto 0 at this stage, you would have post-selected onto having a linear combination of unitaries. But when you're talking about looking at features of Hamiltonians, it's very convenient to just whack a reflection about the 0 state on the end there. Because what that gives you is now something which has eigenvalues which are related to the eigenvalues of the original Hamiltonian. And it's much easier than generating evolution under the Hamiltonian. And what these eigenvalues look like is, so if this is the complex plane, then if your eigenvalue for your Hamiltonian was h, you're going to get something which is slightly scaled. You're going to get an arc sign here in the complex plane in terms of the angle, and you're going to get a pi minus arc sign over here. So you're actually getting two eigenvalues. What we're interested in is the 0 eigenvalues, which would be down here, and we're going to get a symmetric one over here. So this is a +1 and a -1. Or in terms of a phase, it's a 0 phase and a plus or minus pi. So then if we're looking for that, those 0 eigenvalues, the Hamiltonian, you're looking for that plus or minus 1. So then what you can do is a filter on that. So optimal filter ends up looking like this, where you have this strong peak at 0 and a plus or minus pi. And if you can then apply that filter, then that's going to tell you what's your portion of the state which is corresponding to the 0 eigenvalues. And this is something which has a complexity which depends very nicely on the allowable error. That epsilon would basically be the height here. And it also has an inverse dependence on a gap. And you essentially do need to assume that there's some gap to the nearest non-zero eigenvalues, just so that you're not picking up things here which are eigenvalues which are non-zero. And I think I'll skip over this because, well, this is just talking about how to do the amplitude estimation. And the net result of all of this is that you get a factor for the amplitude estimation, which is going like this, where like delta's coming from a the probability of error in a confidence interval. You can essentially ignore that part since it's logarithmic. You also have a 1 over epsilon, where the epsilon is the error in this ratio. Now, the thing which means that you can get some improvements for a larger Betty numbers is that typically you would be interested in measuring things with some relative error. So if you're interested in measuring your Betty number, which is this beta with some relative error R, you're going to get a factor which goes like the number of cliques divided by the Betty number with the square root. And this ends up being multiplied by this factor that we were getting originally for the amplitude amplification, for the picking out the cliques in that initial state preparation. And I've actually simplified things here a bit by dropping off the part for the filtering of the zero eigenvalues. And for the example that I'll be discussing, that is actually smaller than this part. So this sort of gives you a way of seeing what the scaling of the complexity is in a reasonably simple way. And interesting feature of this, you have a number of cliques in the denominator and the numerator, which cancel out, and tells you that roughly you can expect a scaling of the complexity that's going like n choose k divided by the Betty number and then a square root. Now, if the Betty number was of order of a constant, then this would be going roughly like the square root of n choose k. And n choose k, you can regard as roughly the complexity of dealing with this classically. Now, if you were to do, and this is with an approximate classical method as well, where you would be, say, trying to represent things with the vector and use sparse matrix arithmetic on it. So if you had the Betty number being a constant, then you're still roughly getting a square root improvement over classically, which is okay, but we would typically want to get something better than that. So ideally, we'd like to get something that's an exponential improvement with a quantum computer. So to do that, well, not to get exponential, but to at least get something better than a square root, you can look at particular types of graphs. So this is sort of a not quite complete illustration of something where you can have subgroups of nodes. We have connections between these subgroups, but not within the subgroups. And it turns out that the Betty number for this is scaling like m minus 1 to the power of k. And if I remember correctly, k is the number of these subgroups, and then m is the number within each subgroup. And when you work out the estimated classical complexity, it's going like this. You see you have an e to the k, and you have a log m there as well. Whereas a quantum complexity is roughly an e to the k on 2. And that means that if you're looking at this as sort of what is the root there, it's not a square root anymore. You have a 2, and then you have a 1 plus log of m. So if you have m being a constant, then this is sort of possibly a large root improvement. And you can also consider cases where m is, well, if k is increasing logarithmically with n, then this log m is roughly going like log n, and you have a super polynomial speed up. And this is what we get for actual estimates of the gate count. You have a quantum complexity, so this is sort of increasing with the number of nodes in the graph. The quantum complexity, you can see it's increasing really slowly. And this is a classical complexity if you're estimating it through n choose k, or you could possibly estimate it through the number of cliques. And you can see there that both of these are increasing very rapidly with the size of the system. And in this example, this 2 1 plus log m is roughly 7.5. And a root going like a 7.5 root is much better improvement than just a square root. So in this example, it's about 80 billion toffolies. It's a bit more than, well, this particular value of K and M, it's about 80 billion toffolies. It's a bit more than, say, with counts for Shor's algorithm or quantum chemistry examples, but it's still sort of something you could reasonably imagine that a full error-corrected quantum computer could do. But if you look at this dimension, that's going like 10 to the 25. And if you think of how the classical algorithm works, it's actually needing to store that entire vector. So it's not just needing to do a number of gates like that. It's needing to have that amount of storage. And that is a very, very large amount of storage. I think that's sort of more than the total amount of data on the internet or something ridiculous like that. So that's a strong indication that this is intractable classically, though there's a recent paper with some very clever ideas for how to do these classically, which might make it a bit more tractable. Okay, now this is for this specific example, which is sort of with a fixed arrangement of edges where we actually already know what the Betti number is. But there's also examples where you can have some, it has some structure to it, but it's a random choice of graph. So we don't know exactly what the Betti number is in this example. And so this is something where you would need to run the quantum computer to actually estimate it. But it doesn't give us quite the speed up in that case. It's actually a fourth root speed up rather than something which is potentially a larger and larger root for larger systems. So I think my time's about up, and I'll just go to the conclusion slide. Thanks.
Thanks very much. Are there any questions for Dominic? If not, I have one. What? Okay.
Yeah. Yeah. Yes.
So, is there like so that like notes that involves some C daggers for first?
Yeah. So
yeah, so I was wondering like, so is there a relationship between this and like index theory and the zero nodes?
I don't think so. Well, the way I've drawn it here is not actually the Hamiltonian, because I've left off the things where I've filtered the cliques. So the Hamiltonian is drawn there, doesn't actually have any graph information on it. But in terms of sort of how we can do the quantum algorithm, it's sort of this type of thing which we designed for quantum chemistry.
Oh, okay, but is there direct connection between the fermionic representation to information to get out?
I'm not sure what you mean.
Well, I mean, you could go the other direction, write this in terms of fermionic.
Yeah.
What does the analysis look like in terms of fermionic?
Well, you can write it in terms of fermionic annihilation creation operators, but in terms of actual implementation in the algorithm, you then need to do sort of Pauli strings. And as well, it's not just annihilation creation operators. You would then still have to have the filtering for the cliques, which is sort of doesn't have this picture in terms of fermions. Yeah.
Oh, yeah.
This is for a specially constructed type of graph to demonstrate that you can have very large Betti numbers. So the other example is the a Beatty number which ends up giving us a fourth root speed up, and this is also sort of it's a sort of a constructed set of graphs to demonstrate that there's a speed up, but actually finding applications with data that correspond to that is another question. So the collaborators have looked at some things like financial series data and so forth, and were finding that that wasn't really giving very large Beatty numbers, and so it's still a work in progress to find something where it's actually a applications which are giving the large Beatty numbers. Yeah, 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 yeah. Well, we're not implementing the ArcCos. It's just what the eigenvalue happens to be. So if in this case, we're just trying to filter, and the ArcCos just turns a 0 eigenvalue into a plus or minus 1 eigenvalue, which is simple. In the case of, say, quantum chemistry, we were interested in energy eigenvalues. All you need to do is measure the eigenvalue of this cubitized operator, and then this is a simple function which you can invert. So because you're doing that classically at the end, it doesn't really matter that there's an ArcCos in there or anything.
Any other questions? Yeah, Peter.
Well, when we're doing this, we typically don't care about circuit depth because we're having to count the Toffoli gates, and typically you have a limited number of Toffoli factories. So the Toffoli factories are typically needing a fairly large real estate in the quantum algorithm, and you can run Toffoli factories in parallel to generate magic states to implement Toffolis, but your bottleneck is the generation of the magic states, and then using the Toffoli states isn't really that slow. So it doesn't really matter whether things are parallelized or not in actually using the Toffoli gates. Yeah. Yeah, yeah. Oh, okay. Mm, yeah. Yeah. So this what the two methods that I described there, they're not really easily parallelizable because you do need to do things in sequence.